at compensating for faulty visual information. You come up with other ways to balance yourself. Okay? Yeah?
But how come that those oscillations that we saw don't appear in the variance?
They don't appear because actually these ones they're just longer range oscillations. And there's lower frequencies in there. And if you average over a lot of the data, it's not too obvious from here. It's going to do that. Okay. You can calculate all kinds of things. Here's power spectral densities, Hurst exponents for people who know what this means. And you can come up with a model. Here's a model that we just put out for visually assisted posture control. And you have this this is your position, and A1 is positive. So this is basically an inverted pendulum falling over. That's this part. But your ankles are keeping you stable via your spinal cord and your brain. But there's noise in the system. And then there's this kind of adjustment you keep doing to keep yourself straight. You change your equilibrium a bit. And that equilibrium depends on where you are. So S dot depends on your visual delay. And we change this visual delay. And this thing actually reproduces that variance plot that I just showed you. But it's pretty hellish to figure out the dynamics of this thing. It's a two-delay nonlinear system. We've done some work on two-delay systems before. They have these kinds of things called Tokens-Bogdanov points, which are, anything goes. You get all kinds of multi-stability and so on. And that's where we're at with this. Okay, so let me just wrap up. I've shown you some examples of oscillations with correlated input and how basically the spatial scale of the input will be important in determining the kind of oscillation you get. And that's in parallel with the usual stories we hear, which is the temporal range. If you have a resonance in the system, you have to excite it at that temporal frequency as well. But the spatial frequencies matter. And the oscillation strength is going to be proportional to the spatial correlation. And I showed you some formalism for noisy spiking with delayed feedback. I talked about on-off cells, multiple delays, posture control. So for the future, the more loops, the more paradoxes. You can start adding some local circuitry with delays, and you can try and guess what the answer is, and generally I'm wrong. Okay? It's just, delays are just not that intuitive. You can look at large-scale neural activity with all these delays between different parts of the brain. So there's Axel here has worked a lot on this, and we recently published a model on anesthetics, the effects of anesthetics and neural networks with delays, and how that changes the frequency bands and the power at different frequencies. So still a lot of work to do there for 1 million years. And then there's this stuff from nonlinear dynamics that percolates into this area, chaos synchronization, chaos communication, where some feedback loops are controlling other feedback loops. That's for the future. Driven delayed feedback loops. Just the theory of a delayed loop being driven is not obvious, so we're working on that. There's this dichotomy, it's noise, chaos. David Ansel and Sampolinsky, brought this up front for many of us. That's all built in to these systems. How do you disentangle the two? How do they cooperate in some way? And this is the final message, is that a lot of what I've shown you has nothing to do with transients. It's all the steady state behavior. Characterizing the transients and multi-stability when you go from one kind of behavior to a coexisting kind of behavior, that's a lot of fun to think about. Okay, so I'll stop right there and take any questions.